Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 3.1 titled Sets and Subsets. Alright, so we're in the chapter 3 now called Sets. In this first section, I'm going to it's basically a freebie. I'm going to do all the activities for you. In this first one, it's a lot of definitions and a lot of basic concepts on sets and subsets. In fact, I think the first two sections are just a lot of definitions, and then we go into more things later in the section related to sets. All right. So 3.1 sets and subsets, and I'm going to be just reading a lot of this to you, a lot of definitions. Sets play an important role in almost every area of mathematics, including discrete math. Set theory is a well-developed branch of mathematics in its own right, most of which is beyond the scope of this material. Right, so like they're saying here, this is not going to be a chapter on set theory, like a set theory class. Right? It's like this is all like introduction. We'll start with some basic definitions, notation, and ideas related to sets, all of which will be used extensively in the rest of the topics covered. Alright, so some definitions. A set is a collection of objects. It's that simple. Objects may be of various types, right, such as titles of books, names of bridges, or rational numbers, right, all over the place. This material is mostly concerned with sets of mathematical objects like numbers. The objects in a set are called the elements of that set. A set may contain elements of different varieties, right? So a set whose elements are the number 2, a strawberry, and a monkey, like they have later, like a number, a fruit, and an animal. A set is defined by indicating which elements belong to it. If the number of elements in a set is small, like if it's only got 4, 5, 6 elements, the easiest way to describe the set is by just listing those elements. This is called roster notation. The roster notation definition of a set is a list of the elements enclosed in curly braces with the individual elements separated by commas. So the following definition of a set uses roster notation. All right. And I see that usually a set is given a name, right? And sometimes it's a capital letter, like here this is set A equals, and then the curly braces at the beginning and at the end, and then you have 4 elements. This set contains 4 numbers: 2, 4, 6, and 10. And it doesn't matter what order they come in, right? So this set is also set A. It contains the element 10, the element 6, the element 4, and the element 2, the same as this one. So it doesn't matter what order the elements are listed in, as long as it has the same elements listed, it's the same set. The same thing goes for repeating an element. Repeating an element does not change the set. So this set A with 2, 4, 6, and 10, if I have 2 2s, that means I still have the element 2, right? Repeating it doesn't change what elements are in it. 2 and 2, that means I have the element 2, 4, 6, and 10. So these are all the same set. Again, repetition doesn't change the elements you have. Now, if sets have different elements, they're not the same. Right? If I had another set with the number 5 in it, this doesn't have the number 5 in it, so it wouldn't be the same as set A. And they go through some examples here. Right? Set N, and we'll see lots of diagrams like this with circles or ovals with pictures, with the elements inside the set. These are called these are part of what's called a Venn diagram, right? A Venn diagram we'll see later is just a picture representing sets. So N here, has the elements 2, 4, 6, and 10. So I mean this set N is exactly like set A. They're equal. Right? You're going to see sets are equal when they have the same elements in them. Set F here has a watermelon, a banana, and a strawberry. So you have a curly braces, watermelon, comma, strawberry, comma, banana. All right. Hopefully very simple. This set M has 2 strawberry monkey. Right? Yeah. Okay. So hopefully this roster notation is very simple to read. So let's select the statement that is false. Right? So here, set S is the set with elements 1, 2, 3, and 4. It's got 4 elements, 4 numbers. Is S also equal to 4, 3, 2, 1? Yes, they have this set has the same elements that this set does. So they are the same set. How about the set with 4, 4, 1, 2, and 3? It has 4, 3, 2, and 1, just like this set. They are the same set, even though there's repetition. I know you're probably thinking, hey, there's 2 4s in here, there's only 1 4 in there, but they have the same elements though. Right? Repetition doesn't change the elements that they have. So this is also the same as set S. And here set S is 1, there's 3 2s, so it just has the elements 1, 2, and 3. Yeah, there are 3 2s, but it only has element 2, even though it repeats 3 times. Right? But notice that it doesn't have the element 4. Right? So this is not the same set. It does not contain the element 4. Here, T. Set T is the set with elements, lowercase a, uppercase a, lowercase c, and lowercase d. How about this? Is this the same set? It has lowercase a, it has lowercase c, it has lowercase d, it has uppercase a, but notice it also has this lowercase b. This set does not have lowercase b in it, so this is not the same set. Right, that's false. And then these other two here have the same elements. Even though there are repetitions, they still have the same elements, so they would be considered the same set. Okay? All right, so some more notation related to sets. This symbol, it's like a sideways E, right, that I just highlighted here. Looks like a sideways E. It's the Greek letter epsilon. Is used to indicate that an element is in a set, as in 2 is in set A, or 2 belongs to set A. The symbol, that same symbol with a slash through it, means that the element does not belong in that set. So if you read this, this means that 5 is not an element of set A. Typically, capital letters will be used as variables denoting sets, as you've seen up here. Capital T, capital S, right? Capital N will represent the name of the set. And lowercase letters will be used for elements in the set. Again, typically, not all the time. Variables can be used to indicate an unspecified member of a set, right? An unknown member. For example, if little a is an element of set A, then A is equal to 2, 4, 6, or 10, right? Back talking about this set up here. Right? Then little a must be either 2, 4, 6, or 10. The set with no elements in it, the set with no elements and nothing in it, is called the empty set, and is denoted by this symbol. So it looks like an O with a slash through it, or a 0 with a slash through it. That's the empty set. The empty set is sometimes referred to as the null set, again, nothing in it, and can also be denoted by just an empty set of curly braces, right, where I write just the braces with nothing in between them, no elements. Because the empty set has no elements, for any element A is not an element of the empty set is a true statement. Because again, nothing is an element of the empty set. A finite set is a set that is either empty, right, has no elements, or whose elements can be numbered 1 through n. right? So not infinite, right? There's not an infinite number of elements. That's finite for some positive integer n. An infinite set is a set that is not finite, right? So like the set of all the integers is infinite, for example. Another definition, the cardinality of a finite set A is denoted by, now it looks like this symbolism here looks like the absolute value of A, but it's not. All right, the capital A here represents a set, not a number. So it's not absolute value of A, it's the cardinality of A. And it's just the number of elements that A has. All right, so for example here, if A is the set with 2, 4, 6, and 10, right, then the cardinality of A is 4, right? There's elements 2, 4, 6, and 10. That's 4 elements. Right? So the cardinality is just the number of elements in the set. The cardinality of the empty set, right? This little put the bars around that symbol for the empty set is 0, right? There are no elements in the empty set. When there are many elements in a set, it may not be practical to provide an exhaustive list. It might not be, it would take up too much writing or too much time to write the whole list. So in this case, ellipses, which are the ... are used to denote a long, possibly infinite sequence of numbers. And you've seen me use the ellipses when I've written out the integers before. 1, 2, 3, ... However, the sequence's pattern should be clear so that the reader can infer or figure out what elements are missing. All right, so you write out enough elements to where a pattern is obvious, and then you can put your ... So they give an example here. Below are some examples of the use of ellipses to describe sets. So here's set B. It's equal to the set with elements 1, 3, 5, ... all the way up to element 99, right? This is a finite list because it ends, right? It's not infinite. And again, enough elements are written here so that the pattern is obvious. So it's 1, 3, 5, 7, 9, 11. You keep adding to it. It's all the odd numbers from 1 to 99. And this is something I wouldn't want to write all of them out. I don't want to write 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, all the way up to 99. I don't want to write all that. So that's why the ellipses are used. Here's another one. Now this one's infinite. If the ellipsis shows up at the end or at the beginning, it's an infinite set, meaning the pattern goes on forever. So this set C has the elements 3, 6, 9, 12, 15, 18, 21, 24, 27. And I don't want to do that. I can't possibly write them out because it's an infinite number. This is just all the multiples of 3, all the positive multiples of 3. And again, the ... here to indicate it goes on forever. It's infinite. They say here, in the first example, the set B contains all the odd integers between 0 and 100. In the second case, the set C is an infinite set containing all positive multiples of 3, as I said. All right. I've already mentioned this before. Right? Two sets are equal if they have exactly the same elements. Right? So if these sets are defined here, D equals 3, 4, 5. E is 5, 3, and 4 are the elements in E. F has the elements 5, 3, 4, and 6. Then D and E would be equal. All right, see D equals E because for any element of D, every element in D is an element in E, and vice versa. Every element in E is an element of D. But these are not equal to F because of the element 6. Right, 6 does not belong to E. 6 does not belong to D. So F is not equal to E. F is not equal to D. But D and E are equal. Hopefully that's pretty easy to tell. So they have another animation here for you. I'll play this one. So here's a set A with elements 2, 3, 6, and 10 written in roster form. roster notation where you just list them off. And the order does not matter, right? So this is the same set here with 3, 2, 10, and 6. The cardinality of A with the little, like, it almost again looks like absolute value, is 4, right? It's just the number of elements of A. This symbol, right? This little sideways looking this little E looking symbol, it's called epsilon. 2 is an element of A, right? 2 belongs to set A, as you can see here, see in the picture. 5 is not an element of set A. You don't see the element 5 show up. Right? And just getting used to the notation. And then here's a picture of the empty set, right? It's got nothing in it. This, you can either use this symbol, the circle with the slash through it, or the empty set of braces. And also the cardinality of the empty set, right, which I didn't mention, is 0. There are no elements in it, and nothing belongs to it, right? You'd always have the belong with a slash through it for any element in the empty set. All right. So now we're looking at, consider the following sets. Set A has the elements 4, 6, and 3, and that's it. Set B has elements 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20, and it stops, right? But again, they got the ellipses there, but you can fill in the blank. Fill in the ellipses. Set C is has the elements 2, 4, 6, and then 8, 10, 12, 14, 16, all the positive even numbers. So this is an infinite set. And then finally, set D has elements 3, 4, and 6 in it. So they're saying, are the following statements, true or false? Okay. Is A equal to D? Remember, sets are equal when they have the same elements. So A has 3, 4, and 6. D has 3, 4, and 6, and that's it. There aren't any elements in A that aren't in D. There aren't any elements in D that aren't in A. So they are equal. 5 is an element of A. Look at set A. Does it contain the element 5? Is there a 5 between any of these commas? No. So that is false. 5 is not an element of A. 5 is an element of the empty set. Remember, this is the symbol for the set with nothing. This will never be true. Right? No element, no object is an element of the empty set. So this is 5 can't be an element of the empty set. This is false as well. Set C is finite. No, it is not. Right? The ellipses are at the end here. That indicates it goes on forever. It is infinite, not finite. This is also false. The cardinality of B is 10, meaning there are 10 elements in set B. Let's count them. 2, 4, 6, that's 3. Then 8, 10, 12, 14, 16, 18, and 20. If you counted all those, that is 10 elements. Or you can think about it, this is 2 times 1 all the way up to 2 times 10. That's 10 multiples of 2. There are 10 elements in B. The cardinality of set B is 10. That is true. And this is again about the cardinality with the little bars around it. So basically this is telling me that A and D have the same number of elements. What's the cardinality of A? It is 3. What's the cardinality of D? It is 3 as well. So this is 3 equals 3. That is true. Okay. Easy enough. All right, you can read this example on your own. All right, so some symbols that you're going to see. Now I've put up some of these before, like the symbol for the integers and the symbol for the real numbers, the Z and the R there. But if you see this like bold N symbol in this text, it's the set of what are called the natural numbers, which are all the integers greater than or equal to 0 in this text. All right, I've seen some other books where the natural numbers are just greater than 0, not equal to 0. But in this book, when you see this N symbol, it's the integers greater than or equal to 0. 0, 1, 2, 3, 4, 5, and so on. This bold Z, when you see it, is the set of all the integers Right, so again, it's infinite both directions. You have 0, -1, -2, -3, -4, and so on. Then 1, 2, 3, 4, 5, and so on. We've seen how the rational numbers are defined, right? And this is symbolized by a bold Q or a fancy Q. The rational numbers, which is all the numbers that can be expressed as a over b, where a and b are integers and b is not 0. Remember how rational numbers were defined. All right, now I can't possibly list those. Right? They give you some examples, but there's an infinite number. And then the bold R, right, capital fancy R, is the set of all real numbers. So all the rational numbers with all the irrational numbers. All right, so some other notation you're going to see. If you see one of these symbols with a little plus sign next to it as a superscript, that means we're talking about the positive ones, right? So like R plus here is all the positive real numbers. You know, Z plus is all the positive integers, right? And if you see a little minus sign as a superscript, you know, that means you're dealing with the negative versions of those numbers. You know, Z minus is all the negative integers. R minus would be all the negative real numbers. And we've talked about non-negative before. If I say something's non-negative, that means it's greater than or equal to 0. And if I say something is non-positive, that means it's less than or equal to 0, right? They don't mention that here, but... All right, so some more true or false statements. So -3 is an element of z plus. This is the positive integers, so that's a negative integer, so no. 0 is an element of z plus. Remember, z plus is all the positive integers. 0 is not positive, so that's also false. 0 is a non-negative integer. Yeah, 0 is not negative, right? 0 is greater than or equal to 0, so this is true. 5 belongs to R plus. 5 is an element of the positive real numbers. Yeah, 5 is a positive real number, that's true. -5 is a member of the set of all non-negative integers. The non-negative integers would be 0, 1, 2, 3, 4, 5, 6, 7, 8. You know, -5 is not one of those, so that's false. 0 belongs to the rational numbers. Is 0 a rational number? Yeah, you can write it as 0 divided by 1, right? The ratio of two integers where the denominator is not 0. So yes, 0 is rational. All right. So next, so we've seen roster notation, right? Earlier we saw roster notation with the ellipses as well to indicate that, you know, there's a pattern. Or if it's just a really large set that you don't want to write out, you use ellipses, the dot, dot, dot. Here's some other notation that you may be familiar with from like an algebra class. In set builder notation, a set is defined by specifying that a set includes all elements in a larger set that also satisfy certain conditions, right? So certain conditions are written that, you know, the elements in the set have to satisfy. So the notation looks like this in this text. So say here I have set A equals all elements x in set S such that P of x is true. Right. S is the larger set from which the elements in A are taken. P of x is some condition for membership in A, you know, letting you know that something belongs to A. Something that, you know, satisfies this statement and belongs to set S belongs to set A. The colon symbol is read, you know, such that. The description for A would be read all x in S such that P of x, as I said earlier. Often the set S will be one of the standard mathematical sets from the table above, right from this table here. Okay. So for example, this set here, C equals all the integers such that they're between, you know, 0 and 100 and prime. So this is all the prime integers between 0 and 100. That's what this is describing. Set D here is all the real numbers that are, between -1 and 1. Right? All the real numbers that have an absolute value less than 1. Right? It's all the real numbers between -1 and 1. Not including -1 or 1 though, because those don't have an absolute value less than 1. Those have an absolute value equal to 1. All right, so I'm going to actually write these out on some paper here, and we'll see. We are given a set here in set builder notation, and we have to fill in what would that look like in roster notation. All right, so I'll start with the first one. All right, so this is the first set in this activity, and it reads, I called it set A. They didn't have a name for it. I just call it set A as all the integers, right? It's all the integers that satisfy the following condition, right? Such that they're between 0 and 20 and prime. Right, so if I wrote this out in words, this is all the integers that are between 0 and 20 and prime. So let me write this out in a roster form. Right? This is called set builder notation up here. I'm going to write out the same set in roster notation, where I'm just going to list the elements that are actually in this set. So let's think of the integers. Now obviously 0 doesn't belong here, because it's not between 0 and 20. 1 doesn't belong. Remember, 1 is not prime by definition. So 1 doesn't belong. How about 2? 2 is between 0 and 20, and it is prime. Right? Remember, prime means that its only divisors are 1 in itself, right? And it's greater than 1. So 2 is the first prime number. 3 is prime. 4 is not prime. 5 is prime. 7 is prime. 6. All the even numbers aren't prime after 2, right? So I'm not going to mention the evens, because they're all divisible by 2. 9 is not prime. 11 is prime. 13 is prime. 15 is not, right? It's 3 times 5. 17 is prime. 19 is prime. And then I'm too big, right? We're only looking for the prime integers between 0 and 20. So there you go. This is the set A. This set up here is described in set builder notation. Here it's described in roster notation. And just to add some stuff, we can see that the cardinality of A, remember this was how many elements are in A, is what? 4, 8, right? This has 8 elements in it. And just to throw out some other notation, we see that 3 belongs to A, right? 3 is an element of A. See it there. But 6 is not an element of A. Again, just to get you used to seeing me write out some of this notation. Okay. But this is what we want right here. Right? They said to write it in roster form. So going back, that's this set here. Get that in the first spot. Okay. All right, let's look at the second set. All right, so I called this second set B that they have here, and this is all the real numbers such that their absolute value is equal to their square. All right, so every real number whose absolute value is equal to its square. And you can write that out in words if you wish, but I'm just going to go to roster notation here. And right now I'm telling you, I'm just going to, you could do some algebra here, but I'm going to tell you right now, the only ones that satisfy this are -1. Right, -1, the absolute value of -1 is 1. -1 squared is also 1. 0, right, if x were 0, 0 equals 0. And +1, right, you'd have 1 equals 1. And that's it. You can go hunting for other ones, but again, you could show algebraically that these are the only 3 solutions to that equation there. These are the only 3 real numbers that satisfy this. Right. Great. And then, you know, if again, just to throw in some other notation, just to get used to me writing some of this other notation, you know, what's the cardinality of B? The cardinality of this set is, you know, 3. Right? There are only 3 elements in it. And just to, again, and we see that, you know, 0 is an element of set B, right? 0 belongs to B, you see it there. But, you know, the number 5 does not. You know, there's lots of elements that do not belong to set B. Is not an element of symbol. Right, but again, this is what they wanted right here. Right, so back to this. That's this set here. Right. So putting that there. Cool. All right. Now I'm just going to read off these and not write them out this time. Remember this is this set here. This third set is all the natural numbers. So remember, natural numbers start at 0 in this book. It's 0, 1, 2, 3. All the natural numbers such that, you know, you're even. All the even natural numbers. So now remember, 0 is even. So you have 0, 2, 4, 6, 8. You know, dot dot dot. Right? That's infinite. 0, 2, 4, 6, dot dot dot. That's this set. And finally, the last set is all the all the natural numbers that are even and less than 20. So you can see that that's this set here, 0, 2, 4, 6, dot, 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 but that would stop at 18, though. It is a finite set. Right, there are 10 elements in this set. The cardinality would be 10. And again, I don't know why I'm really filling that in, but okay. All right, then your challenge activity. All right, so I'll start it. There's only 4 of these. So it says fill in the missing value such that A is equal to B. So these, you know, remember, 2 sets are equal when they have the same elements. So set A has 1, 9, and 0. So set B, in order to be equal, would have to have 1, 9, and 0 as well. But it has 1 and 0, so it needs 9. Right? Very simple, that one. All right, this is what's the cardinality of A? Remember, this is how many elements are in the set. There's 1, 2, 3, 4. There are 4 elements in that set. Very simple. Another cardinality, but this time the set is written out in set builder notation. So this is, you know, set A here is all the integers. And that's what that Z stands for there. All the integers that are between 2 and 4, but, you know, not including 2, but including 4. So 2 is not included, but 3 would be. 3 is an integer in here. 3 and 4 would be. So just this set is just set with 3 and 4 in it. So that's 2 elements. The cardinality of A is 2. And I think, yeah, this is another cardinality one, right? So I'll leave that. All right, so more definitions, and we get into, you know, again, these Venn diagrams, right? Little circles, pictures representing sets. All right, the universal set, usually denoted by a capital U for universal, is a set that contains all elements mentioned in a particular context. So universal set has, you know, all elements in question. For example, in a discussion about certain types of real numbers, it would be understood that any element in the discussion is a real number. Right? So the universal set would be the set of real numbers in that case. In this case, the universal set would be the set of real numbers. In a discussion regarding the academic standing of certain students at a school, the universal set would be the set of all students enrolled at the school, right? So it depends on the context. But the universal set is the set of, you know, everyone in question, everyone that you're discussing. Sets are often represented in pictures, right, pictorially, with Venn diagrams. So a rectangle is used to denote the universal set, right, the U, set of everything. And oval shapes, or, you know, it doesn't have to be ovals really, but usually in this book there'll be ovals, circles, right? Oval shapes are used to denote sets within the universal set. Sometimes Venn diagrams can indicate which specific elements are inside and outside the set. An element is drawn inside the oval if it is in the set represented by that oval. The following animation describes the use of Venn diagrams. All right, so I'll show you this. So I got these elements. First of all, the universal set is represented by a big box. Then we have this set A with elements 1, 2, and 3 in it. So here's elements 1, 2, and 3. They just draw a circle for set A to make sure that 1, 2, and 3 are in the set. And notice that 4 does not belong to the set, and it's outside that oval, outside that circle. And then here's a set called B with 2, 3, and 4 in it. So again, another circle is drawn for set B so that 2, 3, and 4 are inside the circle. And there you go. All right, and again, all these elements are in the universal set, right? The big square, the big rectangle. That's a simple example of a Venn diagram. Right, and you can very clearly see what elements are where. 1 is in A but not in B. 4 is in B but not in A. And 2 and 3 are in both. You see the overlapping region? And you can see that both elements have 2 and 3. All right. So another definition. Right, lots of definitions in this first section. If every element in A is also an element of B, then they say that A is a subset of B, denoted this way. And it almost looks like a less than or equal to symbol, but it's like a sideways U looking shape. All right, so it's almost like a less than or equal to, but not sharp like a less than or equal to. So this is A is a subset of B. Every element of A is also an element in B. Right? So if there is an element of A that is not an element of B, then A is not a subset of B, and then you would just throw a slash through the symbol. Right. If the universal set is denoted by U, then for every set A, the empty set, all right, this is huge right here. All right. Know this. The empty set is a subset of any set. Technically vacuously, because remember, this is an if-then statement. All right, this here. This is an if-then statement. If every element of A is also an element of B, then A is a subset of B. Well, if you look at this statement here, if every element of the empty set is an element of A, then the empty set's a subset of A. Well, there are no elements of the empty set. So the hypothesis is false. Remember, when you have a false hypothesis, the implication is true. So I'll say that one more time. The empty set is a subset of any set. Okay. And any set is going to be a subset of the universal set, because the universal set has everything. Right, everything that's being talked about. All right. Two sets are equal if and only if each is a subset of the other. All right. So this is huge. This is going to come into play when we go into writing proofs about sets later. Right. So two sets are equal. Right. So A equals B if and only if. This is a biconditional. It goes in both directions. A equals B if and only if A is a subset of B and B is a subset of A, right? And think about that. That means that every element of A is an element of B, and every element of B is an element of A. Okay. So therefore, they'd be equal. Okay. All right. And one more definition. If A is a subset of B, right, and there is an element of B that is not an element of A, so meaning A is not equal to B, then A is a proper subset of B, and you just get rid of that little half equal symbol. So this symbolism means A is a subset of B, right? So every element of A is an element of B, and they could be equal. Doesn't mean they have to be. This symbolism is A is a proper subset of B, so every element of A is an element of B, and they're not equal, meaning there's some element of B that's not in A. Right? So you don't have the little half equal. It's not like less than. It's just like less than. right? And not less than or equal to. And then here's some Venn diagrams showing you. So here, B is a proper subset. So every proper subset is a subset, but not the other way around. All right. If B is a subset of A, that doesn't mean that B is a proper subset. But if you're a proper subset, then you will be a subset. Right? If that makes sense. Okay, so here's some pictures, and again, I'll let you play this animation. I'm going to actually go into the activity, and we'll see. We'll look at some statements. All right. So consider the following sets. A equals the set with 3, 4, and 5 as elements. B is the set with 4, 5, and 3 as elements. C is just a set of odd integers, right? All the integers that are odd. So, 1, 3, 5, 7, 9 going that way, and -1, -3, -5, -7, -9 going that way. All right, that's an infinite set. And D is the set with elements 3, 5, 7, and 9. Right. Is A proper subset? See, it's just like the less than, but without the equal part. So is A proper subset of B? Now, this means, is every element of A in B? Yeah. Right? 3, 4, and 5 are in A. Those are also in B. But they can't be equal. Is there an element of B that's not in A? No. So A is a subset of B, but it's not a proper subset of B because they're equal. See, A is a proper subset of B if and only if A is a subset of B and A is not equal to B. But here, A is equal to B. Now, is A subset of B? It's got the equal to part, so it's not proper. Right? Is A a subset of B? Basically, again, the question is every element of A an element of B? Yes. I just said that. 3, 4, 5, 4, 5, 3, same elements. Every element of A is in set B. Is set C a proper subset of the integers? So first off, is it a subset? Right? In order to be a proper subset, you first have to be a subset. So is every element of C an integer? Yes. But to be a proper subset, you can't be equal. Well, look at C and C and the integers. Is this equal to the integers? No, you're missing the even integers. So this is true, right? Every element of C is an integer, but they're not equal. So C is a proper subset of Z. And again, they give you the conditions for that right up here. What does it mean to be a proper subset? Is B a subset, right? Just a subset, not a proper subset. Is B a subset of D, right? So is every element of B an element of D? Let's see, 4, 5, 3. Well, you got the 5 and the 3, but 4. 4 is in B, but not in D, so no. B is not a subset of D. Is D a subset of C? Again, not a proper subset because you got the little half equal symbol. Is D a subset of C? So is every element of D also in C? Are 3, 5, 7, and 9 also in C? Yeah. C is all the odd integers. These are odd integers, right? So every element of D is in C. D is a subset of C. And also, D would be a proper subset. You could get rid of the half equal sign because they're not equal. Okay. Are the natural numbers a proper subset of the integers? Yes. Right? All the natural numbers are integers and they're not equal. Are the integers a proper subset of the rational numbers? Yeah. Every integer is rational and they're not equal. Right? There are rational numbers that are not integers. And are all the rational numbers a proper subset of the reals? Yes. Every rational number is real and they're not equal. So this is all true. All right. Is the following statement true? For any two sets, x and y, if X is a proper subset of Y, then X is a subset of Y. Yes, I've said that earlier, right? That means all the elements of X are in Y, and that's what this means as well. But this one has the added thing that X can't be equal to Y. But if X is a proper subset of Y, then X is a subset of Y. That is true. Now switch them. Do the converse. Remember the converse, where you just switch the hypothesis and conclusion. Is the following statement true for any two sets, X and Y? If X is a subset of Y, then X is a proper subset of Y. Well, no. What if they're equal? You know, every element of X could be an element of Y, but they could also be equal. And if they're equal, then they're not going to be. Then X is not going to be a proper subset. So this is not true in general. Right, and you can see you saw some examples of that up here earlier. Right. And then you have your additional exercises. Again, lots of definitions and vocabulary and notation in this section. Right. So you got a lot of so you got your exercises here. Some of these, right, are in your assignment 3 that you're going to upload to me. Some of them are not. I still recommend doing all of them, right, just for extra practice and, you know, get used to the notation and the symbolism and the vocabulary. You can also, again, see the solutions if you wish. Please, though, you know, please try to do the problems, work on them before, you know, you look at the solutions and then just see how you did. Because you're not going to learn anything if you just look at the solutions and copy those down. Alright, so that's it for the introduction to sets and subsets. Right, again, lots of vocab, lots of notation. Hopefully you get the hang of those. Right, hopefully when you look at a symbol, you understand what it represents, what it means, and yeah, and hopefully you have a good time. You know, when you go through this on your own and go through, you know, the problems that I've assigned in assignment 3, and even the other problems as well. Right, the ones that I didn't assign. Right, so hopefully you have a good time, get some work done, and thanks for watching.